So good morning, everybody. First of all, I would like to thank the organizers for being so tolerant and so open-minded, because I'm clearly the outsider here. There's no appetite, no calcite, very little bone, maybe one picture with a bone, no teeth, no shark, no fossils, so we are talking selenium now. Still, I think it's very important to consider and very interesting. Why? Because of this. So not because slacklining is such a cool sport, but it illustrates very well the role of selenium, which is an element that is both toxic and essential, and the threshold that is described for being sufficient for your nutrition and causing deficiency is considered one of the smallest of all elements. So you see here there's a factor 10 in between only. So basically we're all walking on a very thin line between deficiency and toxicity. And that's the only picture then of bones here. You see here some deformities that are due to selenium excess and some calcification here of the heart muscles due to deficiency. So the point is that we are all doing this balance permanently, and we have to take care that we don't fall down, because there's death and disease luring on both sides of the rope. So this is a very classical example of selenium contamination. So that is a model that has been developed in the western US called from rock to duck system. So basically you have here selenium and sulfur containing sedimentary rocks. So they are weathering with the time. Selenium comes to the fields, is being used for irrigation. You have evaporation, you have concentration of selenium, bioaccumulation, and at the end you have toxic effects, because it's a strongly bioaccumulative and biomagnifying element. However, if we enlarge our view a little bit and we look a bit more global, we see that basically selenium excess is limited to very, let's say, local settings, like for instance here this Kazakhstan reservoir. But on a worldwide scale, selenium deficiency is a way bigger problem. So you see here, for instance, we have done some risk maps for China. You have here a selenium poor belt stretching through all central China. And you can imagine how many people, if you think on population, how many people are affected by selenium deficiency. So there are some calculations, estimations that up to 1 billion people might be having an undersupply of selenium. That's simply based on crustal abundance, and then people have been considering how much is considered a good supply for human and for animal. And basically there's not enough selenium to reach sufficient supplementation for all people on the world, for all people and all animals, although they are basically the same. So the point that I want to make is that selenium problems are not basically a problem just of toxicity, but simply a problem of distribution. So we need to find methods bringing selenium from a place where there's high concentration. It can be natural contaminated site, it can be also industrial wastewaters, and I will talk about that, to places that are selenium deficient. So another point that is not been considered yet in this estimation of the 1 billion people potentially being selenium deficient is that there's very strong technological development in the field of renewable technologies. And for instance, these 6 cells, so the copper, indium, gallium selenide cells, as the name says, they use selenium. So this is pushed very strongly politically to be developed. And then, of course, you get not only competition between feed and food selenium, but also renewable energy. So it's not like a biocrop where there's competition, but really competition with a technological product. So we think, or we've come to the philosophy nowadays, that just a removal of selenium, like you would do that classically in wastewater treatment, or immobilization of selenium in soil or sediments, is simply not appropriate anymore. We need to have methods ready to recover selenium and to reuse it in other products. And that's what my talk is about. So very luckily, nature gives us some promising tools to do that. And this is what I'm going to talk about now. So there are organisms that, in the absence of oxygen, they can respire selenium oxyanions. So much like sulfate reducers that you all know, or arsenic reducers, there's also selenium reducers. So basically they use any kind of electron donor. They take the toxic water-soluble oxyanion, that can be selenite or selenate. They form some degradation products and a solid selenium biomineral. That's why I'm here. And interesting is that they conserve energy because of that, so it's a respiratory process. So they are self-sustaining if you want to apply them in any kind of technological process. So the advantage if you use this kind of process is that you detoxify, because these oxyanions are considered more toxic than the elemental selenium form. And of course you have a solid form that you can separate, that you can recover and potentially reuse. So I will show you a few works on bioreactor operation. So the kind of system that we've been using in the past comes from anaerobic wastewater treatment. That's called the so-called upflow anaerobic sludge bed reactor. So this is biomass agglomerates, so biomass together with inorganic matrix that are so dense that they can settle and self-immobilize themselves in the reactor liquid. So you have an upflow coming up and only the dense, sticky biomass and particles remain in the reactor. So you reach very high biomass densities. And why we have been using that, you can see here a cross-section of one of the granules treating selenium. So you have here nicely the red layer on top of it. This is some SEM EDX pictures. So these granules, they form kind of microenvironments. So you have niches regarding substrates, metabolic products, but you also protect your microorganisms in the inner part of the granule from the potentially toxic medium in the outside. So you can see here, for instance, the sulfate reducers that form iron sulfides. They are located here in the middle of this granule thin section. So you get also locally niches for microorganisms to thrive. So the first bioreactor operation that I will show you aim to simulate flue gas desulfurization water treatment. So when you burn fossil fuels, the SOXs are washed out of the flue gas, and you gain waters that are very high in sulfate and also in selenium. Well, 10 micromole is relatively high regarding selenium concentration. So we've been operating these usually mesophilic with a very short hydraulic retention time for anaerobic processes, and we've always considering methanogenic versus sulfate reducing conditions. So these are two reactor operations over 160 days that you can see here, and what we've been doing there is playing around with a sulfate load that we would apply to the reactors. So in the first picture here you see in green you have times of very high sulfate excess. So that's where you have this 26 millimoles of sulfate and 10 micromoles of selenate. And basically you see when we switch between low and high sulfate rate, instantly the first time after sampling, selenium removal goes either up or down. So basically here the selenium selenate and selenium removal is coupled to the sulfate load that we apply. The second part is a methanogenic reactor, and we can see here that over a time of 40 days, suddenly you get an increase in both selenate removal and total selenium removal. And that is due to the fact that there's these disinflammatory selenium reducers developing over time. So that's a reproducible effect. You will see later bioreactor run where you see a very similar picture in the beginning. And here it's important to note when we apply the same kind of excess of sulfate, we still have several sampling days that are 100% removing selenate. At the very end you get some fluctuations. This is all a bit squeezed together because it's 160 days. Basically when you have a little bit of sulfide formed, so again here the sulfate reducers are kicking in with the time, then the removal goes down a bit. But we can say that still it's, at least for this period, you can see how selective this process is. So visually, you can try to count these points. So these are 2,600 molecules of sulfate, and there is one molecule of selenate that can still be taken up by these microorganisms and used for respiratory processes. If you consider that these molecules are very similar, I think that's really unprecedented selectivity of these kind of enzymes. So you've noticed that there were two curves. There's selenate removal on the one hand and total selenium removal on the other hand. So selenate, we've been measuring species specifically, and then we have been doing the balance in contrast to the total selenium that was still in liquid. And we were wondering what is this gap that was occurring. So basically what you see here is a gap when you filter your effluent just with a large pore size. You have this is again 160 days of reactor operation. You see here the guys developing and kicking in. So you have a good removal, but basically you have a gap. So there's still some selenium in the effluent after filtration, let's say like this. And we did a very simple approach. So it's sequential filtration with decreasing pore sizes here. And then you get like a particle size distribution roughly of your effluent selenium. So we see that up to a third of the selenium, so all these peaks here, is basically due to the fact that we have particulate selenium in the effluent. And we were looking at that time, it was not so clear, so we were looking at that time on even smaller particles, so colloidal particles that made up to 9% in the effluent. Seeing the pictures from before, it's obvious for you, but at that time it was not clear that you would form really this colloidal, I call it nowadays, maybe nano would be more modern, so this selenium nanoparticles. And of course gravitational settling, so this is the comparison where you have a settler after the reactor that simply serves to increase the retention time and then allows particles to settle. Of course, that doesn't work because particle sizes are so small. We've been looking then a little bit on the biomass that was forming here. That is, interestingly, that is one of the tubes, not the biomass itself. So Teflon tube that was turning red by the time. You can see here a SEM picture. Of course, we find selenium. You have some platinum from sputtering and copper from the grid. So basically only selenium, carbon, hydrogen, oxygen signal. And if we zoom into this, we had a discussion with Christopher, I think, in the very beginning. So there are some microbes that are completely encrusted in selenium particles. We don't know if they are still alive or not. It's always a problem of a mixed culture. Finally, you don't know who does the job. But okay, at least the particle sizes that we find here, so 100 nanometers maybe around, they correspond with what we find in the effluent. So then we were intrigued a little bit by these properties of biogenic selenium. So you see, of course, Lenz, please don't move. When you let the bottle stand, even after 20 hours, you just see a little bit of clarification, but basically they don't settle. We have this nanoparticulate size. We have amorphous particles or not diffracting particles. And when you do a very simple octanol water coefficient experiment, so this is chemically synthesized selenium, this is biogenic selenium, you see very, very different properties between this mineral and chemically synthesized selenium. So we came up with a very basic model. I think for you it's all obvious. For us it was not so obvious at that time. So we think that there's a selenium core and there's any kind of organic around. We did not know if it's proteins, lipids, or whatever, membranes. We did not know. So we had a little bit closer look on what could be these organics and how these organics are determining the colloidal properties of biogenic selenium. So basically we cultivated a number of microorganisms, both respiratory and not respiratory, reducing microorganisms. We isolated the particles so that we get pure particles free from biomass or free from supernatant. And then we try to identify proteins and we determine colloidal stability in different media. This I will show you now. So the method that we have applied is a density-based centrifugation. So the liquid is polytungstate. That is a very dense liquid, so 3 grams per mil. And selenium has somewhat higher density. So with the time, you can separate very well. Here's the biomass after centrifugation, and selenium, it really, at the end, it sinks down to the bottom of that liquid. So by repeating this centrifugation over and over again, I don't know, I think 10 repetitions and then washing and so on and so forth, you really get pure biogenic selenium particles. So we have been doing this with the biomass that has been producing selenium, with biomass alone as control. And we also had a look what would happen if we mix biomass with chemically synthesized selenium. So then we did a SDS page. You can see here these are two selenide respirers, and this is a non-respiratory reduction or organism. So you find a number of proteins basically. Importantly to notice is that the control does not contain any protein anymore. So that means that the particles that we have, proteins that we find, are really due to particle-associated proteins. There's no more biomass, there's no more supernatant left. So that was the first time that we could describe this pure particles and also the particle properties. So when we go then to protein identification, you're not even supposed to read all these proteins. So basically there's a big chaos there. So there's a huge number of proteins. We have been doing very restrictive matching. So we've been kicking out everything that is usually still considered as identified, but still you get huge tables. These are 2 pages in the paper. You have also all kinds of metabolic functions, cellular locations. There's a big mess. However, there's one protein that has been called metalloid reductase. And why is that interesting? Well, first of all, it was the best match. So there was a huge protein score that is calculated. So from 50 on, it's already considered significant match. And why I'm pointing out this one is that it was found the best match on both biogenic and non-biogenic selenium. So there seems to be, or potentially there can be some specific binding interaction. The problem here is that there's nothing known about this protein. It was submitted somewhere and nobody, there's no more information than just the name. So we don't know if it has a really function, what it does. We can just do a blast and we get some similarities with a porine that for some reason makes sense. Of course, you need to bring selenate somehow in the periplasmatic room, but there's no information on this available. So we don't know yet. So a bit refined model is that potentially we have specific proteins that are on the selenium, that are binding on the selenium surfaces, but then certainly you get some corona that is still very strongly associated. You cannot separate that, but it's probably just unspecific proteins that are binding or sorbing there. So from an application point of view or from an environmental point of view, it's now interesting to see what's the impact basically on the colloidal properties of this organic modification or of the corona that you have. So having this pure selenium particles were the first time we were able to determine colloidal properties. You can see here, if you go of the pH range, you see that basically under most conditions, for sure under the conditions that are applied in bioremediation, you have very strong negative charge, so they are repulsing each other and they will never settle. And you can also see that when you're using counter-cations, so monovalent, bivalent, or trivalent counter-cations, you can of course neutralize that charge and induce settling. So when we go for bioremediation, now it's obvious why people have never been able to separate their particles, simply because we are working at neutral pH usually, and at, let's say, at moderate salinities. So this allows also some careful conclusions on the environmental fate of biogenic selenium. That is of course also formed in sediments and soils and so on and so forth. So we see here the colloidal, the zeta potential measured in 2 artificial lake waters, where we are just at the border, what is still considered colloidally stable and what is considered colloidally unstable. We see that in sea waters there's a high salinity, so basically you will get unstable suspensions. And when we go to organic rich, so we have been using different humic acids, we get even a stabilization of that suspension. So when you think on environmental transport, well, in acid mine drainage, it's maybe even positively charged. Then here you are on the border of the colloidal stability field, so maybe you have settling, maybe not. But then basically when you go to marine environments, it will sink, or we suspect it to sink to the bottom and to represent also sink for selenium as well. So then the next step was then, okay, now that we know the colloidal properties, we can influence them to recover selenium really from the effluent. And it's a very simple experiment. So we have been using calcium concentrations in this case that would correspond to 0, 15, or minus 30 millivolts. And basically when you apply already this medium concentration, you get very rapid settling, so 80% within 1.5 hours. And that is interesting for application because it means the footprint of your reactor will be just a quarter of what is the actual bioreactor. So you need to have short settling times in this case. So regarding costs, I did not take calcium here as example, but I took the worst case. So even if you buy in some strange internet portals, you can find lanthanum chloride for around $2,000 per ton. It would require 10 to the minus 4 molar of lanthanum. Of course, you would not use lanthanum for settling, but it's simply the worst case. And that corresponds then to like $7 per cubic meter that you would need to invest for this polishing step. So when we look to other biological processes, we are already like 20 to 50, 60 US dollars per cubic meter. This means that you add basically very little on the price, considering that you would not use lanthanum, of course, but calcium or whatever. We can also think of using, for instance, zinc from other waste streams, because zinc is an element that is equally deficient around the world, so you could even then reuse that as a fertilizer or as in biofortification. So then I come to the summary. I have no clue how many minutes I spent. Well, I will continue anyway. You cannot stop me. So selenium problems, the point that I want to make, I mean, not only the dose makes the poison, but also the dose makes the deficiency. So selenium problems are simply problems of distribution. We need to find methods to bring high concentrations of selenium to places of low concentration, let's say like this. We can see that these disinhibitory selenium reducers are extremely effective and selective for selenium reduction. They form a solid bio-nanomineral. This bio-nanomineral consists of a core that is selenium, but basically the protein corona gives the properties to this bio-nanomineral. And we can see that under normal bioremediation conditions, the suspension are colloidally stable at neutral pH, at moderate salinity. So if we want to induce settling, of course, we need to do some polishing of the effluents. So we can manipulate that to basically to steer recovery of selenium. So then I would like to thank all of my colleagues, and just I've been spamming you already. We are organizing a special session on the 6th European Bioremediation Conference. So you can just Google this because the internet page is quite complicated. We will have Tom Hannibal from Berkeley giving the invited talk on platinum group, biogenic platinum group, nanoparticles. So I think it will be very interesting, and if you find any kind of relation of your topic for resource recovery, biomineralization and resource recovery, or new biomining technologies as well, you're very much invited to come there and to join the discussion. So thank you for your attention.